So good morning, everyone. It's a pleasure to have you here. And also good morning to the audience online. This conference is run in hybrid mode, so I hope everyone can enjoy it, whatever way you choose to follow it. For the audience online, microphone and camera is muted, but we will have some interaction poll, and you will have the opportunity to ask questions and comment through the chat box. The workshop will be recorded and available afterwards on the Cultural e-channels and online. Here is the QR code to join the Slido. We will have some warm-up questions. So let's try this out. Where are you joining us from? Let's see. Somebody from Brussels, I think is from the audience here. Somebody online do not want to state his position. Some colleagues from Bolzano. Venice. Let's see if we have other countries joining in. From France. Somebody is both in Brussels and Copenhagen. Is that you? Madrid. Think, did more or less anyone replied? The first one always takes a little bit longer until everybody is on. Okay. So you can move on if you want. Yeah, I can move on meanwhile. What is your profession? Architect, researchers, some engineers. Some more engineers. That's look quite good. We have some actors, some players also from the construction sector. So after this warm-up, I will move forward since we have quite a tight schedule. Let me present myself. I'm Annamaria Belleri. I'm the project coordinator of Cultural E, and I work at EURAC Research, which is a research center based in Bolzano, Italy. We are having today some presentation of the first results of this Horizon 2020 project on PlusEnergyBuildings that have been running now since more than 2 years, and we have also still 1 year and a half on the way to end. The project aims at overall increasing the market uptake of PlusEnergyBuildings, and how we do that by bringing new tools and methodologies and developing further existing technologies in order to reduce the cost of PlusEnergyBuildings and make them more affordable. As you know, positive energy buildings are not something new, but in the past it has been something that had a cost, and now we aim to decrease that basically. What is a plus energy building for us? It is not only a building that produces more energy over a year than it consumes, but it is also able to have a dynamic match between load and generation to increase the self-consumption and to reduce the energy grid congestions whenever it's needed. And also to, and it does that at the lowest gas emissions possible. It is also has an added value for us in terms of health and well-being of occupants, providing a good indoor environment quality and a dynamic indoor environment quality. And also it provides easy access to e-mobility. How can plus energy building become the new building standard? These are the pillars that we bet on at the beginning of the project. So to put the user and household at the center, trying to understand their needs and to guide them towards better energy practices, to define viable and interoperable technology concepts, to have an integrated climate and cultural approach. That's why the name of the project, that's where the name of the project came from, and also to define business models that are attractive and that considers also this added value of plus energy buildings. This is an overview of the overall approach. We first map what are the cultural and climate differences, and on the website, an energy atlas, a 2-cup energy atlas is available, containing some interesting information for designers. Then we have 5 key technologies that we are further developing. The house management system, cloud-based, so we are storing and analyzing data on the cloud. It's also taking advantage of other buildings information and comparing this with them. We will have an active window block, easy to install, but also which that includes several functions such as smart shading controls and also exploiting decentralized passive and active ventilation devices. We promote the use of smart air movement to reduce the cooling need of the building. In the project, we are also developing a decentralized packet heat pump able to provide heating, cooling, and ventilation in a compact, all in a compact unit. And then we are developing strategies for energy flexibility. All of these technologies are then combined in solution sets that are adapted and tailored to each climate and cultural geocluster. And then the aim is to demonstrate those in 4 buildings around Europe and to use them to promote and increase the share of plus energy buildings. Here are the demo cases. We have different demo cases in the 4 geoclusters that we identified in Europe, and all of them has a different, let's say, business model related, since we have a private social housing company, Vilogy. We have a public building for assisted living in Norway. We have a private real estate in Germany and a private cooperative in Italy. So this is the overall agenda of today. So after my welcome, we'll have a round of pitch presentation from addressed to each technologies, and then we will present how we are combining them into solution sets, and also we will present the way the climate and cultural drivers we identified for the plus energy buildings and the overall life cycle environmental impact assessment of that. And hopefully in the end, we will be able to have a short Q&A session and a lunch. So I hope you will enjoy these few hours. And I leave the word to Jose for the next presentation.
Thank you. Yeah. Thank you, everyone. Yeah, thanks, Annamaria. Thanks, the audience. Yeah, I'll introduce the first technology that we have developed in the project. It's the cloud-based house management system, and how we foresee the interaction with the user, taking into account all the different constraints and limitations we will have. Well, first of all, which is the objective of our cloud-based HMS? Well, of course, the initial one is the monitoring and the indoor environmental quality evaluation, so that we demonstrate all these plus energy buildings. Also, of course, the indoor comfort, how to evaluate and demonstrate the improvement on that aspect. And of course, the user acceptance. That is, the system will be there, so how the user, and when I refer to user, I'm not only referring to the tenant itself, but also the building owner, facility manager, any other user that will be a stakeholder in a plus energy building, will accept and will access the technology. Of course, the HMS is ensuring the interaction with the technologies that will be introduced later, that have been developed specifically during Culturally project. So we ensure interaction between the different building energy systems. We enable advanced control strategies, take into account that this cloud-based system is not, of course, physically installed in the building. So we will take advantage of what a cloud infrastructure can give to us in order to improve control strategies in a dynamic way. And also to demonstrate, of course, the performance of the other Culturally technologies that will be, as I said, introduced later. So the interaction between user and HMS will be the key point. I mean, the user will be part of the loop and not the final destination. So we will use this interaction to understand users' needs and preferences. So by design, we have developed the cloud-based HMS in a flexible way to be adapted to user needs. In terms of access to data and to all the different services, but also on the way we present information in a clear way, so that they understand the message, they understand how they can get the benefit of using this HMS. So we will, of course, present meaningful information on energy consumption, indoor environmental quality. And last point, but not least for sure, the goal is to engage users toward better energy practices, better energy usage. So, of course, as in all the other technologies, the HMS will be tailored and will be specifically adapted to each demo case based on physical constraints, physical architecture, and of course, business model as well. So this is a typical IT architecture. So I wanted to include this into a slide to show you how we conceive, how we see a building from this cloud-based perspective. So for us, there are different segments, from the dwelling up to the floor, building, and finally the cloud. So from the cloud, we are able to communicate bidirectional to any of the devices that are installed at the dwelling level, at the floor level, and at the building level, so as to ensure control is capable of managing all the different loads in a coordinated way. So this is the, as I said, the IT architecture. So we must ensure the cloud is able to cope with the different communication protocols, the different devices, data loggers, PLCs, etc., that will be installed in the buildings. We have not forced pilots to follow a particular architecture to make them compatible with our vision of the cloud-based HMS. But what we try to do is to adapt the cloud-based HMS to the typical communication and control architecture that we can find in any building. So we don't want to have 4 pilots with a very nice, very appealing IT architecture, which are hard to maintain beyond the end of the project, or hard to understand for the facility owners, for example. That's the key point for us. So basically, the message with this slide is from the cloud-based system, we are able to connect to the building through a single connection, so as to ensure security at that level. We are able to control any of the devices, monitor and control any of the devices, and once data and once services are running in the cloud, we are able as well to cooperate with external services. You can think of weather forecasting services that are available from external providers. You can think of third-party service, for example, energy prices providers, so that we can include that information in the cloud. We can even think of exposing some connectivity to apps in which, for example, the owners, the real estate, whoever wants to exploit this data in a different way, we will do during the project. It will be also possible. So the cloud infrastructure we have deployed, it is a scalable cloud infrastructure. So we have not defined an infrastructure specifically for the project, but for the scale up of this solution. So I will not go into a lot of details, but just to mention some of them. We have a private cloud environment. So even if it is if the cloud-based HMS is running in the cloud, it is a private environment. So no one can access without, of course, security and credentials. We have different machines running. So it's not one single server. It's a bunch of different machines running different services to ensure 24/7 availability of service and data and, access. The data is stored following an non-SQL database, which is basically, the message is that we have a replica set of the database. So even if in the case of a catastrophic situation in which the database is not available, we have 3 different machines replicating the same structure. So it automatically it would switch the database from one side to another. All the connections between the building and the cloud are encrypted following, in this case is AES 128 encryption. But anyway, the message again is the communications are encrypted, 1-to-1 and 1 versus 1. So it is not possible that anyone could see the data that is transmitted from one point to another. Also, data is anonymized when it is installed in the database, in the cloud. And this is made by design. This is not something that runs in a service that encrypts the data, but it is part of the definition of the database. So the features the cloud HMS has, well, of course, the initial one is the collection of streaming and batch data. I mean, we have support for different protocols. The idea is that either we have real-time streaming data being communicated to the platform, or we receive batch data from, for example, some SCADAs in a file format. We are able to cope with this. We are able to perform, as I explained, massive storage, retrieval, and management of data. We handle graphs, data aggregation, and filtering of data. That is, that with the raw data coming from the building, we are able to perform basic calculations like data cleansing, for example, like in the energy consumption monitoring field. Sometimes it can happen that you don't have all the data as you were supposed to have, for example, receiving data every 15 minutes. So in that case, we have interpolation capabilities. We also offer the possibility of doing data fusion, basic data fusion for calculating indicators based on the raw data coming from the building. We have also created a SCADA editor so that we can define appealing views of data. As I said, we are not only considering the user as the tenant, but also as a facility manager or whatever. So all the stakeholders should be able to check the data as it is, as they want to get this information. And we will be running machine learning components for forecasting, improve building control, and so on. So finally, just to summarize, we are providing a cloud-based system compatible with all the different field solutions we are finding in the pilots, but also in real world. We integrate user interface for the different kind of users, especially occupants, towards better practices, and also in the assist of the usage of the technologies, control systems, and basically it will act as a central brain for the control of indoor comfort and other kind of control strategies. Okay, it seems we have, I have a question. Do you think our solution complies with data security and GDPR? Yeah, well, as I explained, by design, we conceived this HMS to be secure, because we understand that one of the main barriers to reach residential buildings market with this cloud-based infrastructure are the data concerns, security concerns. And of course, as with any other cloud service, we must comply with GDPR. So it's as well ensured. There are two participants typing. I don't know if we should wait. Okay, yes, it is. Okay. I place. Thank you. Okay. Which benefit do you see in moving to a cloud system instead of having a typical control solution? I guess this is a question for the audience. Okay. Okay. Okay, remote.
Yeah. Meanwhile, I can introduce the next speaker. Meanwhile, we are collecting replies. Next speaker is Giovanni Toniato from Eurofinestra. Is one of the companies that joined the consortium of Cultural E, and they are together with the research team of the project developing the active window system, developing and manufacturing actually the active window system. So he will give us first taste of it.
Yeah, I think audience got exactly the message I wanted to throw. Yeah, of course, a cloud system has all these benefits, and also I would add that the good of having a cloud system is that we can implement services that we cannot even think about at this point with minimum intervention at the building level. So yeah, thank you.
Thank you, Jose. So Giovanni, the floor is yours.
Okay. Okay. Good morning, everybody. Thank you, Annamaria, for your introduction. As Annamaria said, I'm Giovanni Toniato from Eurofinestra, Italy, and together with EURAC, we are working on the active window system. As the name shows, the active window system is a window, basically. Why active? We can call it active because we have designed it with the purpose of making a window that can, in a sort of way, control and manage the internal comfort parameters and also energetic parameters with an active role in the building comfort and energy management. Basically, it's based on 4 principal points. We have designed it starting from a modular wood frame, and we of course chose wood because we work with wood and we think that it's a futuristic material, the ancient and the futuristic. The wood can allow us to set up a frame that we can easily change and adapt to different climate solution. With small changing, we can fit the Mediterranean climate to the Nordic climate. Wood is a natural and renewable material, and it's really easy to modify it to fit all the condition and to give it special features also to resist to the external external climate and to the external climate. We have think to different solution also to that. It integrate an adaptive shading system. The idea to integrate it's based to manage the shading and put it in a position that can easily to maintain and easily to interact with the window system. It also has an integrated ventilation device. It could be mechanical or it could be natural. And as 4 point, we are trying to give. We did it. We make a interaction between the shading system and the ventilation device to try to exploit the best from the energy that we can manage through the sun shading and through the ventilation device. Of course, we don't design a specific product, but combining all the possible solution from the different climate, the different possibilities of shading, and the different possibilities of ventilation, we set up a catalog of 33 different solutions, all based on the same principle and with the same goals. yeah, all the catalog is published and you can take a look at it. How to manage all this complexity, because when we put different system in one, we change what the window usually make, and it's a passive element that manage the light, manage the thermal factors, manage the sound insulation, air tightness, water tightness, and we put other stuff like shading and like ventilation. We have a tons of different parameters, and it's easy to lost. I think that a big step we did in this project is to put together the specifics parameters of a window as U value, G value, and other parameters. Of course, there you see only the principal, with parameters specific of the room, of the comfort of the internal room. Then we put together and we find a road to put everything together, managing the normal parameters that you associate to a window, and also to the parameters associated to the internal comfort as indoor air quality, parameters of ventilation, daylighting, and the thermal, not the thermal parameters only of the window, but of the room. How to do that? We have with EURAC worked on a FEM simulation to design the different frame and the changing on of the frame in the different situation and in the different configuration. We also managed CFD analysis to understand all the possible risk that you have when you put a shading system in a different position from the usual one, and when you try to make this interaction between ventilation and shading system, and also CFD analysis to understand how these element interact and what is going to which type of change create on the internal room. Also working on the shading control to giving an algorithm that can improve all the parameters that we want. At this point, we are basically ready to make the prototype, and we have defined which type of solution we would like to prototype. Of course, in the catalog you can find from the easier solution to the complex, and I think is the main goal of the catalog, to give different solution to different climate requires and to different requires. Not everybody needs all the system, but we give a good solution for each request. About the demo, the demo case, the 3 demo case, we are finalizing the design, and we are going to complete a CE marking for the easier version of the product. Basically, it's the product made of this frame that can scalable and adaptable to different climates. Not only the frame, but also the glass, but the glass, it's easier to manage. Defining also the installation way in the demo building, and the system will be connected to the HMS. Stop.
Thank you, Giovanni. Do we have some question, Paul, here? Not really. So there's maybe some time for question if you have some short one. Nothing online. Okay. So we can move forward. Last minute change in the agenda. We will postpone this presentation because we have an online connection. So I will leave the word to the next one. Could you please go forward to the presentation on smart air movement, which will be presented by Giulia Torriani, a colleague from EURAC, who is part of the team working on defining guidelines for smart ventilation with the use of ceiling fan. And we have here also a technology provider, Vortice, an Italian company working on the product development of that. Thank you, Giulia.
Thank you, Annamaria. Yes, I'm Giulia Torriani from EURAC, and I'm here to present smart ventilation through ceiling fans. So, in a warming climate, for sure, energy demand for cooling will increase a lot in the next years. So it's necessary to find efficient, passive, and low energy solutions. So this presentation aims to put in evidence the fact that air movement through ceiling fans can be an energy efficient way to provide comfortable cooling in warm and hot environments. And in particular, the ceiling fans can also minimize the use of more energy intrusive systems such as air conditioning, for example. In particular, recent studies proved that the ceiling fans can reduce the space cooling need in the Mediterranean climate by 49%, in the continental climate by 91%, in the oceanic climate by 45%, and in the subarctic region by 88%. But this is not all the situation. In addition to that, the elevated airspeed is proven to also impact perceived air quality. So it can really be a good solution for indoor environmental quality and all its aspects. So as part of our past projects, we developed an algorithm which can automatically adapt a ceiling fan rotation airspeed based on the temperature and relative humidity values that can be measured in a room. However, proper testing and validation in real scenarios still needed to be conducted. So as part of culturally project EURAC Research with the University of Venice and Vortice performed an experimental campaign during this summer. What did we ask ourselves? First of all, does air movement improve thermal environment and indoor quality acceptability in residential buildings? Then we asked, does automatic algorithm work in terms of resulting comfort? And then, is there any significant difference in people's answer between manual and automatic control? In order to answer to those questions, we performed a climatic chamber experimental study in our lab in Bolzano. We used two climatic chambers, which were set up as residential environments, so as living rooms. Participants were experiencing 3 different temperatures, 27, 29, and 31 degrees. And we asked them to fulfill questionnaires while we were monitoring the environmental parameters. The sample was composed by 30 adult participants. So we could answer to that question, yes. So air movement really can improve thermal environment in residential buildings. And in particular, we could see that there can be real benefits until 31.5 degrees. After 31.5, we have to say that the air movement provided by ceiling fan does not seem to be really enough to guarantee thermal satisfaction. And we could also calculate the temperature at which it is really necessary to switch on a ceiling fan, and this temperature is 27.6. The automatic algorithm seems to work really well in terms of resulting comfort. So on a thermal comfort point of view, the percentage of satisfaction is higher than 85%. On an perceived indoor quality point of view, higher than 82. On a perceived air movement point of view, higher than 58, and on a perceived soundscape, higher than 77. Then we asked ourselves, is there any difference according to the ceiling fan mode? So what are the different modes? Speaking about control, the modes are the automatic mode, so the algorithm mode, and the manual mode. And then there are two flow directions mode, so direct mode and reverse mode. Direct mode, it means that the hair movement comes from the ceiling and goes to the floor, while reverse mode, the air movement goes from the floor to the ceiling. We could see that the automatic mode seems to differ very little from the manual mode on a resulting comfort point of view. It means that people, the automatic algorithm can predict really well what people want to do. We could see that the direct flow mode seems to work better than the reverse flow mode, and that the automatic algorithm is also able to increase natural temperature in summer of 2.3 degrees. And this is really important on an energy point of view. To conclude, we could see that ceiling fans are an effective way to provide both comfort and energy saving in warm and hot indoor environments, that they can also complement or replace the use of more energy intensive cooling systems such as air conditioning. It was developed a comfort algorithm to automatically control the fan speed. And then the important part is that the comfort level achieved with the automatic control is the same that people experienced when they had manual control, but without requiring them to do any actions. So thank you.
Thank you, Giulia. Is there any slide or rise?
Probably yes. Okay. Okay.
Granite. So how will the climate change changing the energy demand of the households, in your opinion? Or energy requirements for cooling system, that's correct. Or that's what we don't aim for with a smart air movement.
While you wait for the audience to write this, I have a question from the audience. So somebody asked, can the algorithm choose the normal mode or reverse mode?
No, the algorithm for now it is just used for the direct flow modes. And we also have to say that we could see that in summer the direct flow mode it is for sure the best mode to use a ceiling fan. The reverse mode it can be used, but in winter in order to destratificate the air inside a room. So for that function, the reverse mode can be also considered a good flow mode.
Thank you.
Thank you.
There is already another question. Interesting to know the effects of direct and reverse airflow. Would the results be any different if the ceilings have an exposed roof or not?
Okay. Yes, I think that there can be a difference. We didn't study it yet, but it could be a good point for a future study, because I think that there could be a difference. Yes, for sure.
Yeah, curiosity, since you mentioned this real experiment with a sample of people, so I was wondering about the representativity of this sample. It's not so many people, and how do you pick them in order to represent the situation of Italy, or it's more like people living in Bolzano, or the age structure, things, if you can give some detail.
Yes, thank you for the question. It was really difficult to find a sample at the beginning. We decided to have a sample which is representative of Bolzano area. We wrote eligibility criteria, and people needed to fit into those requirements. So the age was from 20 to 60 years. People without particular diseases, because their perception of thermal environment had to be the same. People who were not performing too much sport but at least they needed to perform some hours of sport per week. And also an important eligibility criteria was about where people lived in the last 6 months. We required people to live in Bolzano or in similar areas, or in the Apennini, or in Lombardia, or in places which have the same climatic, with the same climatic zone, microclimate zone. Yes. But we have to say that at the end, the 90% of people were from Bolzano.
Being aware of time, but I still have two more questions.
Okay.
But it seems to be the super interesting technology for the audience. So somebody asked, have you evaluated also the discomfort from air draft? And the other person asked, what was the height of the rooms in your test?
Okay, allora, air draft, there weren't air draft inside the room because it was a climatic chamber and the windows were closed, and the UTA was monitored in order to not to have that kind of problems. But I would like to go to that slide because we monitored the perceived air movement. So we asked to the participant if they were satisfied of the air movement or not. And it was a result too. So at higher indoor operative temperatures, the satisfaction was not really high, we must say, because the speed was higher, of course, in order to guarantee a good thermal environment. So the perceived air movement was not guaranteeing a lot of satisfaction. In fact, you all can see that the air movement seems to be the real problem in terms of resulting comfort.
Okay, thank you. And the height of the room in your testing chamber was?
3 meters.
Okay.
Yeah.
So maybe we can say if there are any other questions from the online audience as well, you can always, there's one more, but you can also just email us and we're gonna reply by email as well, right? Yes, please.
Hello, I'd like to know, how are you doing a verification that your test results are independent, and with which certifying body are you working?
Yes, thank you for the question. Independent in what sense?
Your test results, who can certify it's independent and scientific? Who can verify that it's independent and scientifically based?
Okay. You mean,
do you use a verification service?
Yes.
A third-party test body, and if so, whom?
No, we don't have we don't have a certification body for that.
Mm-hmm.
I would have to say this is a first. Yeah. Yeah, this is not a test that can be accredited somehow as it can. Okay, then we can discuss it later. Really interesting to hear that.
Thank you. My question, I put it also in Slido. What was the height of the rooms where you were testing? Because here, if I imagine fan, it will be not good for some person.
Yeah. It was 3 meter high. Yes. Yes, because in Italy, regulation for indoor rooms where you can live, you have to have ceiling higher than 2.7 meters, so 3 meters.
Yeah, actually, to comment on that.
Yes, it depends on the area. Yes.
Yeah.
Yes.
To further comment on that, it is a limitation of the technology that we acknowledged since, let's say, the beginning of the project, because it can be, and it proved to be an alternative to cooling system, and the highest potential is actually in the northern and the continental climate now, because it really can be an alternative to AC systems. But the issue is about the ceiling height, so energy efficiency regulation requires lower floor to ceiling height, and this is something that we have to work on to re-engineer the product in order to fit into those height. Yeah. Okay, I think we can move to the next presentation.
Thank you for your attention.
Which is about enabling building flexibility in PlusEnergyBuildings. And the speaker is Enrico Dalla Maria, a researcher from EURAC Research as well. And he's going to present the work that and the results that have been come out from this research carried out together with SINTEF Research Center based in Norway. Thank you, Enrico.
So thank you, Annamaria, for the introduction. As you can see, here we are going to see the, let's say, basic concept of energy flexibility. So we first start from a definition, a very generic definition. Energy flexibility can see as the capability to adapt to a behavior, given, for example, an external input or external requirement. In this sense, such a generic definition may apply to several levels of the energy of energy system. Let's say on the left, you can see, for example, grid, district level, building level, component system level. But here in the presentation that I'm introducing now, we are seeing energy flexibility decline only to the building level and component system level. At this level, we are going to see if it is possible to change somehow the consumption behavior and to aim at reducing some kind of objective, always in the framework of PlusEnergyBuilding. Therefore, we are driven by the same final objective that are environmental and cost reduction. If we have to think at an objective that we have to introduce in our work. In this sense, it's possible to find a kind of theoretical definition of the possible action that may be put in place to practically actuate the energy flexibility. On the bottom left, you can see consume less, therefore energy efficiency, and on-site renewable generation, that are the two components that are somehow embedded in the building and may enable actually the local production and the reduction of consumption of the building during its operation, let's say. Whereas on the right, we see consume differently. For consume differently, I mean the change in the way we can imagine the user interact with the building or the building itself. Therefore, the devices that are present in the building may change their operation. We can see here the keyword are modulate, load shedding, load shifting. These are keywords very related to the, let's say, electrical point of view. Therefore, to the load profile connected to the load consumption of the whole building, the devices, the appliances, and so on that are inside the building. Here we can see two different contributions. I already introduced them. On the left, you can see a positive contribution, therefore production from photovoltaics or building integrated photovoltaics. Then there is also the production introduced by the energy storage system that will shift the actual PV production in case that the renewable energy does not match with the actual consumption that the building is experiencing in that moment. On the right, we can see the loads. Here I present a subset, a reduced subset of loads that are heat pump, electric vehicle, and another time energy system, energy storage system, therefore static batteries. And this is the most energy intensive loads. And on the other side, they are another key advantage that they have on board a controller on which we can operate, on which we can act to induce the energy, the change in energy consumption that we see in the previous slide. As you can imagine, Annamaria introduced already that we are working exploring the potential in different geocluster. All the subset of devices that you see in the previous slide have different potential are within the four identified geocluster. These potential are identified both from state-of-the-art literature and from low profiles, from the low profile that are acquired from other simulation that are performed in other tasks of the project. The final key point of the current slide is that we bring all the components present in the house, and so all the consumption behavior, consumption pattern that compose the overall load profile of an house to an electrical domain, therefore an electrical load profile. This electrical load profile is important as we can introduce into the control logic. In the current slide, we see two different approaches. The starting point is a rule-based control logic that operates substantially the electrical storage system according to the overproduction. Therefore, when there is overproduction, the battery is storing the amount of that energy that is generated but not used in that instant. And on the other side, it acts as a buffer and gives the energy to the building when we have no local, not sufficient, let's say, local renewable production. This kind of algorithm is the state of art, we can say, and is very good at maximizing the performance regards self-production and self-consumption of a building, and it's very simple to implement. Therefore, this key point is very important. On the other side, we may imagine that we can define different objectives, for example, cost reduction, and therefore we require a more sophisticated environment to both produce prediction related to energy production, renewable energy production, to energy consumption, and to other factors that may impact the actual energy profile of the building. And we need, here we call advanced control logic, or you can call model predictive control. Therefore, you have to run the simulation, run the virtual model, let's say, of the building, and check if it's possible to maximize a given objective, for example, cost reduction. It's clear that such a shift in the control paradigm introduces much more complexity in computation and system requirement that must be justified by the actually outcome and performance. Now our work is to perform simulation on that kind of scenario. Therefore, we set up a simplified model of the building and run a long-term simulation on the length of 1 year. And we check if it's possible to minimize some kind of objective. If, for example, we can see some preliminary outcomes that show that with different kinds of model predictive control, we can achieve a reduction in the energy consumption from the grid during the so-called high price hour that we define according to an external signal. Here the key point is that we have an external signal on which the objective function is based, and we try to minimize this cost function. Finally, I spoke of simulation, but our final target is to bring some of the devices and technology that we see in the previous slide in our experimental facility at EURAC Research in Bolzano, Italy, and to try to match the following point, that is somehow model validation, and check if it's possible also to port to existing devices some of the logic that we develop only in simulation. This is my last slide, so thank you for attention. I don't know if you have question, because I have no slide after. So yeah, I see.
Thank you so much. I wondered, this is, I mean, my question is a little bit based on the experiences from practice in Denmark. So we're subarctic, little sun, yeah. Very cold, and so on. We find it really, really hard to do. I mean, it's okay to design, you know, energy neutral buildings in operation. Mm-hmm. But the problem is that when you factor in the embodied carbon in solar cells, in the building fabric, it doesn't look so good.
Yes.
Particularly for PVs, that if you look at market shares, are usually based on production by coal in China. Yes. And in our environment, these are never paid back environmentally.
I think that they may be payback, but it takes many, many more years than, for example,
it's more than the service life.
Exactly, and this is the reason also why we are exploring all the devices and technologies in different geocluster. Because, for example, in subarctic region, also the CO2, the equivalent CO2 emission connected to production of energy is very, very low. So if you set up a function, an objective function, to minimize the CO2 emission, is very, very difficult to do something with the devices, because it's very low. So yes, this is the reason why we explore the different potentials.
Yeah, and I think we will deep this topic with Roberta's presentation afterwards. So if you can hold on a bit on that. And we can finalize the round of presentation of technologies. We have a last speaker online, which is Rob Morrison, Managing Director of Ventive Company, who is going to present the packet heat pump system with a hybrid storage capacity. And yeah, he will explain better what it is. Rob, can you hear us?
I can hear you, yes. Yeah. Okay. Do you want me to share my screen to present?
No, we see the slides, so
okay.
You don't need to.
Okay.
And great. We can hear you very well. Thank you.
Brilliant. Brilliant. Okay. Well, thank you very much for having me today. It's great to be part of this endeavor. We can jump straight into the presentation. All I can see is culturally, do I have a control, or do I just request you to forward the slide?
You can request it, and then Larissa will sort it out.
Okay, great. If we could go to the first slide, please. There we are. So yeah, so we've developed or are developing a technology to enable the energy transition. It's a fully integrated system that will provide heating, hot water, some cooling, and importantly, aid the energy transition by helping to level the load through peak hours and spread into off-peak hours as much as possible. So next slide, please. Yeah, the challenge, as we are largely here to address, is the energy transition. It is a very complex problem from both the generation side and the demand side. We are looking at very much the demand side in association with building fabric, which we obviously have to take a view on. We feel it's very important to achieve a high level of building fabric performance to enable the energy transition, but we understand from a practical perspective that it's not always that possible. So we've developed a solution to help address many of the issues associated with bringing lower performing buildings into electric heating. So we can have a look at in a second. But the biggest question that we have is how we can make it sustainable and manageable in a way that local economies, local distribution networks, installers, and indeed manufacturers can comply with the growing demand from a building regulations perspective. Next slide, please. So we've developed a couple of different types of units. They're all self-optimizing energy platforms that will take up to and including all of the load of the building, control it through its own building management system, and deliver intelligent comfort into the building. So a little bit more complex perhaps than the traditional way of heating, but we've embedded a lot of processing capacity within the units to be able to understand and also to learn and predict weather patterns, to compensate for different and changing weather, all in one box. So it has a full mechanical ventilation with heat recovery system in the B model. In fact, next slide, I can take you through the product. So we have three models. The exhaust air heat pump is built for certain markets that are looking to place heat pump technology into a new build, and some retrofits that haven't quite managed to achieve a decent level of air tightness within the retrofit itself. It provides renewable heating. It uses a centralized exhaust ventilation system to extract air from the building to create a healthy environment indoors. Natural makeup air will replace the exhausting air and allow the building to stay healthy. But obviously, normally with a centralized mechanical exhaust system, you would have a huge energy loss through convective heat loss. Now, we will pass the airflow through a heat pump and extract a large proportion of that heat that would normally be lost to outside. We will then put that heat into a phase change material block at the base of the unit, which will give us a significant amount of energy storage. And that will then be directed back into the property for space heating and hot water as well. All the systems have, as I mentioned before, significant processing power, and they stream data to the cloud. So all of the units can be remotely monitored. They have a significant amount of sensors inside the systems, from environmental data, so CO2, relative humidity, internal temperature, external temperature, duct temperatures, then more kind of intrinsic data from a performance perspective, from a unit performance perspective, which is more like airflow, pressures, things like compressor temperature, starting to work on predictive maintenance, and also be able to track when systems are running in their peak performance mode, or if there's anything slightly off. There are a number of flags that can then be raised through that, or by using that data, to ensure that the performance of the system itself is optimized, and importantly, the performance of the building is optimized. Further down the line, as the market matures, we can then offer a load leveling service to the grid, based on us being able to reduce demand and shift either side of peak, but also being able to utilize overgeneration. And we would intend in the future to bid for capacity in those various markets as they start to grow and develop. Next slide. So that first unit was an exhaust only unit, similar to centralized mechanical extract ventilation. The Home B is a balanced air handling system. So it's based on exactly the same platform, but we've added an additional part to the top of the system. And that gives us full mechanical ventilation with heat recovery. So you can see the additional duct is a supply duct, and that indicates air being supplied to a central or communal area. It can also be supplied to individual rooms. The reason we've shown it to a communal area is because, again, it's subject to air tightness of the building. If you have not achieved significant air tightness, you would struggle to balance the airflow well during the through the building by supplying and extracting from each individual room. You're better off supplying to a centralized area and exhausting from each room. You would get some makeup air coming through from infiltration, but the risk to supplying to each room means you can end up pushing warm air out of the building through the cracks, etc. So there's the initial difference. Now what the introduction of a supply air through the system and a balanced air handling system allows us to do is to give an element of cooling to the supply air based on creating and hot water during the summer. So if there's a demand for hot water, the thermal energy store, or the TES, at the base of the unit will call for heat. We can create that heat by using the heat pump via the extraction system. And then we can, but then obviously as a result of creating that hot water or that heat store, we'll produce cools as a byproduct. So this allows us to redirect that cools back into the property to take the edge off some of the overheating risks in the summer. Now, obviously, it's a byproduct of heating the thermal energy store, and therefore can be classed as free cooling, as it's a byproduct. It's not an air conditioning system, just to be clear. So there we have the same energy storage. We've got the same exhaust air heat pump system that operates in the high efficiency band. As we're extracting at 19, 20, 21 degrees from the house, maybe a little bit higher, and then supplying. Yes, indeed. Sorry, I'm overrunning my time. I didn't realize the time had run on. Again, same load leveling performance we can offer. Next slide, please. Next step is to develop this into a full hybrid system, incorporating the ability to switch between an exhaust air handling system and an air sourced heat pump. This allows us to deal with larger loads, and again will increase efficiencies. You can see here that the PV has been linked up to the box on the system. This is one of the benefits of having all of the utilities effectively in one place in terms of hot water provision, heating, because we can manage the flow from PV. If it's not being used by the building, we can help to direct that into the heat store. Next slide, please. Performance monitoring is critical. We have, as I said before, a lot of sensor points. I think there are over 40 data points within the unit itself, not including the environmental monitoring within the buildings as well. Things like CO2, relative humidity, and temperature can map performance to the design intent. And then we have things like compressor temperature and speed of fans, and things like pressure within the airflow to see if we've got an issue with the filters, for example. So a number of red flags can be provided through the system over time to allow us to monitor that performance. Next slide, please. There are a couple of interfaces that we've started to develop, which will allow real-time monitoring. Critically, a client who is looking after multiple buildings, or a landlord that owns multiple flats or buildings, will be able to dial in and see performance data, have a look at historical reporting, and if they are wanting to be able to optimize the system to their own preferences and that of their tenants or occupants. It also allows them, as I said, to start to forecast maintenance programs, which is a very, very high cost issue for landlords, as I'm sure you'll be aware, and also facilities management companies. So the easier we can make their lives, then the more likely this technology is to commercialize and scale as quickly as we intend. Next slide, please. There is, as you'd expect, also a resident interface that we've been developing. This is purely to allow set point control for temperature. That is the single most important factor for our clients. And let's be honest, it's all about comfort and cost. So we allow them to manage their own comfort. The system takes care of optimizing that comfort provision, whether it's drawing energy from the grid in peak times or off-peak times is largely down to the system. Next slide.
Sorry, Rob, we really need to close since we are running super late. So can you please finish the presentation? Thank you.
Okay, then that's all I need to say on the matter. You can see the bullet points on the right-hand side. That's what we're addressing. It's an all-in-one system designed for the European market and built here in Europe. Thank you.
Thank you. Thank you, Rob. Yeah, I don't know, we'll skip the Q&A session at this point and move to the next presentation and beg for your patience since we have scheduled the other 3 presentations and we might run a bit late. There is some food there. If you're hungry, make yourself comfortable. And I do hope you enjoy the rest of the event. Next speaker is Francesco Isaia from EURAC. He is going to present how we are combining and analyzing the overall performance of these technologies into reference buildings for the new residential sector in Europe.
Thank you. Thank you, Annamaria. Yes, I will be as short as possible since we are not a bit out of time. But yes, with this presentation, I wanted to wrap up a bit what you already heard at the beginning of the session. So you have heard about all the different technologies. You have heard what a positive energy building is. So here, what I will try to do is show you how we try to run some performance analysis to consider these different technological solutions, and how we are we're trying to harmonize all the control strategies to make sure that all these solutions work together and don't work one against the other one. So beside the demo cases that you saw, we also developed these building archetypes. So a low-rise building and a high-rise building, which could be representative of common buildings across Europe of 2 different types. Of course, it's something that needs many has limitations and needs many assumptions, but it was a way to consider 2 building typologies. And the inputs that were taken into account in each building archetype were, I mean, very related to the cultural project. So considering the different geoclusters. So for example, U values of the windows and of the envelope, and also the G value and U value of the windows were different across the different geoclusters, and as well as the temperature set points. And for example, regarding the internal gains, they were based on statistically defined, and they were based also on different geoclusters. So all these inputs were taken into account in the two building archetypes, and were considering these 4 geoclusters that you also saw in the previous presentations. And so I'm not going to go into details about the HVAC system, but also regarding the mechanical system serving the building, we also took into account all the blocks that were into the system, from the storage to the production with the heat pump, and everything was like modularly taken into account. And so the result of this, you can see preliminary results of this performance analysis, is that we could assess all the performance indicators that we also talked about before regarding a positive energy building, considering these 2 different archetypes in different geoclusters. Something that was also needed was considering different solution sets. So how do we combine these different technologies that you saw before in a way that, I mean, we could combine them in different ways in order to reach the positive energy building target. So in this case, we hypothesized two different solution sets, one more centralized and another one more decentralized. And you can see, I mean, I'm not going to go into details of this table, but you can see that in these 2 solution sets, for each and every geocluster, and for, in this case, is the low-rise building, in this case, in the high-rise building, we try to understand what was the best performing solution in each aspect. So in the air movement aspect, in the production of hot or cold water to make cooling and heating, or for domestic hot water production, what was the best strategy, best option in case of centralized and decentralized option. So we made these 2 solution sets, and the results you saw before were related to these 2 solution sets. And what we are going also to do, just for next steps, we are also releasing these 2 building archetypes, like actually the files that will enable users to run some simulations, and we will give users the possibility to change a bit solutions and some inputs in order to see how changing something, it's the positive energy building target can be achieved, and what impacts it has on the energy consumption, on the environmental quality, and so on. So that's a next step we are working on this in this sense. While regarding the control strategies, which of course, I mean, it's in the same sphere of interest, but it's a bit of a different aspect. You saw before that each and every technological solution has its own logic. For example, the ceiling fan control shown before by Giulia, or the shading system control, which Giovanni was talking to you about regarding the active window system. Every system has its own control strategy because it needs to work in a way. So the question here was, like, since we have all these technological solutions and of course many sensors in the building, how do we get this information and combine them together and make sure that they all work in harmony? So of course it's not an easy task to tackle. But our approach is that of course, with the objective of maximizing thermal comfort and the indoor air quality while trying to minimize the energy consumption. Our approach is to consider some hysteresis at the beginning. So hysteresis in the sense that we have to make sure that we don't send control signals every second. So we have to consider some dead bands, let's say. Then consider some schematics that tell us different ways in which our overall technological solution set can work together. So these schemes are going from one mode to another, which are separated blocks, let's say, and then internal modulations, which do some fine tunings. And together, putting all these elements together, we directly send a control signal to the system. So what we will produce also in a next deliverable is all these sets of schemes and fine modulations that will enable us to finally control our system in order to have all the technological solution working in harmony instead of one against the other one. I actually had a question to the audience, maybe I think it's in the next slide, that was a bit related to the control part and was, as a user, like imagining to be a user in a building like this, what would you prefer a control system to do? Like, would you like it to directly choose for you and implement a control action because you think it's the best thing to do and he knows what to do and you think it's the best option, or would you like to have control on it? Or if not, if you answer others, please suggest some other approaches. Yes, but because when we, try to harmonize all these and we try to imagine control strategies, we think that we know what is the answer and we want to implement that answer. But the reality then is that maybe users are not that happy, let's say, in letting the system do what it wants, and sometimes they want to take control. So I think.
And speaking about users, we'd like to introduce the next speaker, which is Ralph Horne from RMIT. RMIT is the partner we've been culturally working on building up the scientific background that we need to understand the climate and cultural drivers that will give us hints to improve the PlusEnergyBuildings
design.
So thank you, Ralph.
Thank you for the answers. That it's not exactly what I was expecting, so it's quite interesting. Thank you.
I have an answer for you, which is that it depends on the day of the week and what is happening. Can you hear? Okay.
The green is to go.
So thank you. I'll be as quick as I can because I know we are behind time. Also, I should say I'm not the best person to give this presentation. The best person is Ivan, who unfortunately couldn't make it at short notice. And I've been supporting Ivan, but I'm not the major person doing this work. So that's my main excuse for not being able to answer any questions. I would like questions. I will take them on notice. I will try to answer them over time, but perhaps not immediately. So as Annamaria says, we are, did I get the right one? Yeah. We are leading work package 2, and I was sitting there at the back listening, and I was late arriving as well, which didn't help. My plane was late, so sorry for that as well. The thoughts going through my mind were that we very rarely talk about actually people. We know it's in our mind when we're talking about building performance. It's always there. We're not just building empty objects, but we have to make assumptions about what people want, just like that last question. Otherwise, we can't do what we need to do. So this is a very genuine dilemma which has been at the center of energy efficient buildings for 50 years. So it's not a new problem. It's a very old problem, and I think we all come at it from our various different angles. From my point of view, having moved over to building sociology from perhaps a more technical starting point of life cycle assessment, I tend to adopt a social practices approach to buildings, which is that the idea of how we use and occupy buildings is not actually behaviorally driven. It's not consciously driven. It's driven by the rules, the meanings, the knowledge, which we have picked up over the years and which we think is the right thing to do. Often we're acting on behalf of others. We're caring for children or others. We're thinking about what kinds of things they would want in the building, not just ourselves. So it's not just a conscious, personal decision set. It's not about a series of digital prompters saying, warning you that you're using too much energy, or giving you hints as to how to use less. That's part of it, of course. All of these things are part of it. But really, there's a need to bring together these very different disciplines. And I'm going to skip through the next few slides pretty quickly. But a central kind of tool, design tool that we are trying to produce through this project is the Atlas, which is a combination of data sets from climate data, but also what we'll call cultural data. And that we hope will build up over time. And I'm not going to speak to these slides because I know time is against us, but I'm assuming that everybody can see these slides and can direct questions if they wish to. I'll skip this one. So two real aspects here. One is a set of information designed to specifically provide, if you like, design advice for designers of all sorts, architects, but many others as well involved in building design processes. And then a set of kind of, if you like, as I mentioned, this cultural data. The idea is that we will draw on data from across different work packages, and that process, of course, is already underway. We will have these different layers of information which we have been compiling to date. I do want to get to the slide on interviews. Here we go. So just briefly, my understanding is that over 20 interviews now have been complete across 3 of the study sites, not obviously in the buildings themselves, but in similar sorts of energy efficient buildings, to provide us with an initial kind of set of qualitative accounts from building occupants about what kinds of things might be going through their mind when prompted about how they use or adapt to these kinds of highly energy efficient building technologies and situations. And we are literally, I have transcripts now. We're just at the process of starting to analyze those transcripts, which will give us a first kind of set of insights. So in order to kind of come back to my initial point I made about this sort of 50-year problem of figuring out, we know we don't want a building that is entirely controlled by users, and we know we don't want a building that is entirely controlled by automation. We know it's somewhere in the middle, but the reality is there are so many different aspects of control that need to be mediated, and which is why I made that joke at the beginning. It depends on the day of the week. It depends on whether I have visitors. It depends on whether I have a cold or whether I have just been to the gym. It depends on so many different factors as to what I might want from a building at any one moment. So how do we provide design up front that will deliver flexibility, but not at the expense of energy efficiency? This is the kind of the idea of the Atlas is a living document that we can encourage practitioners to add to over the years with rich cultural data around users, so that as those practices change over time, because of course they always change, every single thing about how we use, particularly residential spaces, has changed just in the last 20 years. And will change again over the next 20 years, irrespective of climate change and energy efficiency. So it's about thinking about this in a kind of dynamic and live way. Have I run out of time? I'll stop. Thank you.
Also interesting to listen to you, but we have still one last presentation, which is about life cycle environmental impact. And here is Roberta di Bari from the University of Stuttgart, also partner of the project and supporting us in an LCA assessment. So Roberta, the floor is yours.
Yeah, thank you, Annamaria. And I have the luck that so many things have been already told during these sessions. So first of all, starting with the motivation of our task, what is leading us. We are aware of this pandemic situation and also now this energy crisis, and also previously the Global Status Report 2021 already called for urgent application of measures for decreasing emissions and energy consumption in buildings, and already previously in the past, passive and zero energy building offer new perspectives aiming to this carbon neutrality by 2050, which is our goal. Just remembering the Paris Agreement, so everybody's committed to reach, or the whole the society are call it for reach by 2050, the carbon neutrality. And there is now an increasing interest also in PlusEnergy buildings, which has, of course, as a first feature, decreasing operational energy consumption. But on the other side, we are decreasing operational energy consumption by adding new components or adding the amounts of materials and installation components. And here again, photovoltaics, we are increasing the surfaces of photovoltaics, and therefore it's always important to find the right trade-off between the operational emission, but also the increasing embodied emission. And the LCA, the life cycle assessment, is the standardized tool which allows us to analyze the life cycle environmental impact and to finding or to having these trade-offs. Our activities in Cultural A started with an agreement of methodology because we are really connected with mostly all the tasks and all the working package. So it was really important to have an agreement on the methodology. And then we started with the LCA of the previously presented technologies. And afterwards, and this is the current status, we provided a parametric LCA for the solution set. The next step will be, of course, carrying out the LCA for the demo cases for the PlusEnergy building. And looking at the LCA for cultural technologies, here the main goal of the analysis was, first of all, comparing the innovative technologies with also the traditional ones and identifying some improvement potential and provide some feedbacks also to the developers. And this is the example of the Eurofinestra active windows. We are not disclosing all results of the LCA, but just collecting the results and aggregating the results by assembly. And if we are looking to the Eurofinestra environmental profile and the global warming potential of the Eurofinestra, there is in the overall a good environmental potential, but still there is an improvement potential looking at the ventilation machine, at the shading system. While we are looking to the LCA of solution set, of course, we provided a parametric modeling. So we have, first of all, defining all the components which can entail the solution set, and then assess the environmental potential, but also explore the benefits and the challenges in different climate and cultural contexts. The case study was the same of the previously presented, the solution set, designed one for the low-rise 3 floors building, and then the high-rise 7 floors building, each one located in 4 different climate and cultural contexts. And the LCA was carried out by considering the product stage and the end of life based on the information of the building and installation planning, and considering also the operational energy use coming from the building energy simulation. Specifying the LCA analysis, we consider the impact over the whole building. So by considering as a functional unit the square meter of net floor area per year, and analyzing the environmental assessment over 30 years lifespan, meaning we are not considering any replacement of each component, and we consider some environmental databases which are generic, but also for construction sector, the German OCOBAU data, but also specific data sets coming from, for instance, the environmental product declaration. These are the results of the LCA looking at only the embodied impact. And here the results, it's pretty surprising, not really surprising, but anyway surprising, because it leads us to a dilemma. So almost 90% of the whole embodied impact belongs to the photovoltaic, which is then a question for us, but also an answer. So it is like a chicken egg situation. We are adding embodied impact, but thanks to photovoltaics, we are also able to decrease over time the environmental profile, the total environmental impact of the building. And if we are looking here also to the total embodied impact, if we are looking to the low-rise building, there is a higher potential in comparison with the high-rise building, but this is mostly due to the surface, which in the low-rise building is of course less than in a high-rise building. And then looking at the operational impact, of course, we consider the 4 different profiles, the 4 different national energy mix, and the results coming from the energy simulation and the energy balances. And as a result of the energy balances, assuming also a predefined or pre-sizing the photovoltaics, we notice that it's not always ensure the positive balance, or it's easier to reach the positive energy balance in a low-rise building in which we have less user and less energy demand. And in this sense, we can also reach, considering only the operational phase, we can also reach a positive environmental profile, while this is not possible in a high-rise building. I would like to focus now in a low-rise building and considering then the overall life cycle and how it, let's see how we started emitting CO2 in the atmosphere. And this starts today in 2022. This is the first initial environmental investment, and then over time, we can decrease the total environmental profile of the total global warming potential of the building by avoiding CO2 emission coming from the national electricity mix, and by using instead the electricity coming from the photovoltaic system. In this sense, we can calculate also the environmental payback, which is the time which is necessary to pay back the initial environmental investment. And what we did here was also calculating a dynamic payback period, because of course the electricity mix is changing over time, and the EU provided already some scenarios for the next years until 2050. And then we carry out the analysis until 2050. And as a result, what we are looking here, that Italian and German demo cases are the cases in which is it possible to pay back the initial investment related to the installation set only by 2050. While in the French and the Norwegian cases, this is not possible. The strength is slower. But if we are looking here previously, there is the reason. The reason is coming from the environmental profile of the national electricity mix. The France, as we are aware of, as a nuclear baseline, Norwegian hydroelectric. And in this sense, we can say that the payback period are really affected by the carbon intensity of the current national electricity generation. Concluding the presentation, so wrapping up what we learned today, there is a possibility to find really strong differences between the performance level of solution set for PlusEnergy houses, and the effects can be related to 3 main factors: the design choices, the cultural and climate context, as well as the national energy generation. Design choices, and here again, the photovoltaics are the main responsible of the total embodied impact, but also the building type can dictate the operational energy, and within a high-rise building, it's not ensure the positive energy balance, and therefore other surfaces should be spotted around the building envelope. Looking at the climate, cultural context as well, due to lower temperatures and annual solar hills in continental and subarctic area, there are less energy credits, and what we notice is that also in the continental subarctic area present higher user-related energy consumption, but this is coming from the currently collected statistical records. Finally, last but really not the least, this is the really the biggest problem, the national energy generation. So in the overall, we can claim that where the national electricity mix is still carbon intensive, the plus energy houses can be an opportunity for improving the environmental profile of the building in a first instance, but also on the higher level, improving the overall environmental profile of the national energy mix. All the analysis should be, however, conducted on the higher levels, so on the building levels, because we are now showing that we can pay back the CO2 by 2050, which is a good news. But unfortunately, when we are looking at the building level, this is not always, this is not completely a good news. I consider here 3 typical scenarios according to the DGNB system, which is the German environmental certification system for sustainable constructions. And within this system, there are 3 reference buildings which are provided. One is the reference building based on the current praxis, and then there is the target building, which is the building which can achieve eventually a environmental certification, and then there is the DGNB Target Plus, here is called it here, which can reach the highest certification of environmental sustainability in buildings. If we are recalculating here the payback period, the year of the payback, it's really far away, and this is not reasonable, this is not possible. But if we are looking at the Target Plus building, it's still reasonable. 2070 is not that bad in comparison with the reference building. So I would like to also to raise some questions, some doubts on the design choices, which can really affect our main goal, so the climate neutrality and reaching that by 2050. And in this sense, I would like also to ask you some questions which are related to the discussion that I provided in my presentation. So as a designer, architects, are you aware of the consequences related to the design choices and embodied impact? Because we talked so far really a lot, but it's also justifiable. It's clear that we spoke mostly of building operation.
Yeah, short question.
No, there are 2 points that also, if you consider the path toward decarbonization, all the countries in Europe should sooner or later improve their energy mix. Mm-hmm. So if you consider the constant energy mix, you can have some results. But if you consider that also Germany and Italy have to improve their energy mix towards a more decarbonized energy sector, that payback period could extend, not because they will look much more similar like France, let's say, not because they're using nuclear, but because they must give up fossil sources. First point. Second point is in the analysis considered that also to produce photovoltaic, the energy mix is going to change. So you see the carbon embodied is higher in photovoltaic, but also under the production point of view, there will be an improvement. So that you will have these 2 effects that, so yes, are these taken into account, or will be, or can we do this?
There is an answer to this. Our assumption was really conservative, is that, and we consider in the LCA the average technology of photovoltaics as they are today done. So this is an analysis based on what we are emitting starting by today. What will happen in the energy mix, this is still conservative. our approach, because of course, probably increasing the amounts of photovoltaic would also increase the energy mix. But assuming that it's not possible to renovate or to provide the installation of photovoltaics in a huge quantity, we are getting that value, that years. So of course, these are assumptions, but these are assumptions that are due to the current situation. And this makes even more urgent our call. So if we want to implement the plus energy houses, makes sense to do it as soon as possible. Please.
Yeah. One last question.
Thank you so much. One takeaway is that if you add to that payback time, that living up to the Paris Agreement, we have this decade, so there's a carbon budget. If you take that into account, what you have to achieve is plus energy with a minimum of materials, really. I mean, because it's the material dimension, you know, for investing in energy supply systems and reducing the energy usage in buildings. Those are the two material dimensions. And I take away that we really need to do these embodied carbon assessments in all practices in order to achieve that.
I do not understand if it's just a reaction or a question, because I agree totally with what you. The problem is that these are the policy recommendations, and there are also studies that are investigated on the carbon budget, and if it's really reasonable, the carbon budget are reasonable as they are now stated. I am afraid to say that not all the study prove that they can be achieved, and we should probably even more increase our efforts for find other strategies. Let's see what will happen in the future, but as what is going on in the building LCA community, there are a lot of questions, a lot of problems regarding the CO2 budget and the embodied impact. But in the other hand, we should also consider that if we want to reduce the CO2 emission, this probably may mean bio-based materials, using more and more bio-based material, and then cover or asking also if we have enough resources for covering the demand of buildings that will anyway increasing by time, since the population is also growing. So these are a lot of questions, but if we want to focus on the CO2 and to the buildings and to the current situation, we should really find other strategy which should cover the energy generation processes, but on the other hand also a more aware consumption of resources. So this is the combination.
Thank you, Roberta. I think it was a good final presentation and conclusion on that. I think we have to close now. We really thank you for staying up and following everything. I think the lunch is outside. Veronica? It's here. Okay. The lunch will be arranged here, so I'll look forward to meet you there. Thank you all. Bye. And thank you. And thank you to the partner, the Architects Council of Europe, Veronica and Larissa, and also Gloria, who worked in the past days for organizing the event. Thank you.